Okay, let's dive right in. So the goal here is still to look at as few variables as possible. We want to look at only a single axis, so we're not going out and doing tricks and flipping and rolling and doing all of that. We want to do just one move, and we want to make an aggressive a move as possible to stress the PID controller out and see how it reacts. So this right here is what absolutely everything boils down to. Forget prop wash and wobbles and everything else. The entire goal that we're trying to do with our stabilization loop is to make these two lines be the same. We're looking here at the RC command in red. This is our stick command, and the gyro here in blue. And this is what the quad is actually physically doing in the air. So just like in the last video where we looked at the target and the set, this is exactly that. And if our PID controller is tuned well, the gyro, the motion of the quad, not the motors, the PID terms or anything like that, the motion of the quad will match as closely as possible to what our command is. Keep in mind that there's scaling going on and there's expo. Even if you set all of the logs to no expo and stuff like that, there is scaling that the log viewer here is putting in here. So these are not necessarily, the lines won't necessarily line up right on top of each other in this case. Right here, we're only about 9 degrees a second off. So these straight lines here are actually just about on top of each other, and this is a match. So to see exactly what's going on, we have to look at the actual numbers, but you can still tell by the general shape of it what's going on here. Now, the graph that I have here at the bottom is the PID error, which shows you the distance between where you're at and where you're going to. So the PID error here is showing that our gyro is lagging behind what our command is. So the command is we're asking it to go faster than it's actually going. So this is showing us how many degrees a second we're actually trying to get it to go. So you can see here, really obvious on the initiation of this roll, and this is just a snap roll, 360 degrees around, and then a recovery where we have that overshoot that we talked about from too strong P and not enough D damping it down. So you can see we start asking for the roll, and we peg our sticks right here, and it takes a little bit of time for the motors to spin up. And for our gyro, this is not P term, this is the gyro, to start to catch up to what we're doing. And you see right here at this point is when we're the furthest away. We're asking it to be spinning 660 degrees a second, and it's only spinning 500 degrees a second. So that's when the error is the most. And right where we have this overshoot, you'll notice the PID error all of a sudden drops into negatives as we are further away from our set rotation in the air than we're asking it for. And we're going 1200 degrees a second, and we're only asking for 900. And we can also see here on the recovery, I don't have any overshooting on the recovery, but it's just bouncing a couple times where I just let off the stick smoothly and then it's holding at 0. And you can see on the gyro trace that it decelerates really quickly, and then it kind of plateaus for a second here before it clicks in to meet the final one. So that's where you can see we have our most error here is the stick is moving away from our gyro and it starts pushing in, and then partway through it actually catches up and we hit our target. So right here, these two lines are right on top of each other, and we're doing about 115 degrees a second, which is exactly what we're asking it to. But then the stick keeps going away, and the our rotation, our acceleration of rotation has slowed, so we're no longer keeping up with the stick, and then we fall behind again and do before it stabilizes eventually at the very end. So this isn't oscillation. We're not overshooting like we are at the beginning. Here you can see we passed through our target and then come back to it. This is just stopping too early. So what I'm looking at here is the motors, my roll, PIDs plus gyro in the blue as usual, and the PID error. So remember from the previous video, the basic idea, the two PIDs that we mostly care about are the P term, which is in red, and the D term, which is in yellow. And remember that the P term is going to be based on how far away from the target is, and the D term is going to compensate depending on how quickly we are approaching that target. So here we're at idle, and we're just coasting at the top of the thing. We have no inputs put on any of our controls. And as soon as we start inputting the roll, notice the PID error starts climbing. And as this error is rising, you'll see that the P term is starting to push down as well. Now I have a lot of expo on my controls, so you'll see I've got my stick most of the way over, but we're still only asking for a fairly small change in speed. And what happens is when I get to the very edge of the stick, all of a sudden we're going to ask for almost 900 degrees a second of rotation. And once the expo really starts kicking in, you'll notice that the D term starts pushing the same direction that our P term is as well. So our target is getting further and further away from us. So our P term is pushing harder and harder. But as we get into this range of expo, the target starts moving away from us faster, and it sees that the target is going far faster away from us, so it starts pushing as well. And that ramps the two motors on the one side to almost to full speed to initiate the roll. Now, right about there, we're almost at our maximum command. And you'll notice both the terms immediately flip to the other side. And our error passes 0. It goes the opposite direction. So right here we have our most amount of error. We're asking for the biggest difference between what our gyro is actually giving us, 400, almost 500 degrees a second, and we're asking for 650 degrees. So we've got 150 degrees of error that's trying to compensate. And so we're still accelerating at full force. And right here, where the error crosses 0, minus 10 degrees, we're asking for 890 degrees a second of roll, and we're getting 899. So right here, we are at exactly the speed that we are asking it from this PID commands, and you'll notice that the P term has dropped to 0 and the D term has dropped to 0 because we're right at our target. But because we have gained so much momentum, we overshoot, and you'll notice this error dips down, and now we have 320 degrees a second of error the other direction because we're asking for 900 degrees a second of rotation, and we've over-rotated, and we're at 1200 degrees a second of rotation. So the PID controller sees again that we're moving farther away, and if we zoom in really close, you can see the D term starts moving ahead of the P term because the D term sees that we're moving away from our target. So we are actually at the target here, and we only start accelerating away from it afterwards. So the D term sees we're moving away and starts reacting, starts pushing us in the corrective direction sooner than the P term. The P term takes a little while because it only sees the distance that we've traveled, and right here we haven't traveled any distance, so the P term is still very low. But as we get further and further away, and we're up at 250 degrees, now you'll see the P term is really high again and pushing us the opposite direction. So we're spinning too fast, and we're going to get a short little burst of throttle there to recover, and that will drop our error to almost 0, and what this means is we are now at our target velocity, or our rotation speed. And then through all the rest of this flip, we're just coasting on idle power. This entire initiation of the spin is only about 100 milliseconds or so. So we start from 0 degrees a second, accelerate up to 1200 degrees a second, and then slow back down to 900 degrees a second in that very, very short period of time. And we're idle for a lot of this time, and this is a very light, that's only a 3-inch quad with 30-20 bi-blade. There is not a lot of power here, but we still have tons of authority to spin, and we're nowhere near the capabilities of spinning speed that we're getting out of this. Now, on the opposite side, we're going to end the spin. So as soon as you start letting off the stick, and you'll see I've only let off the stick just a little bit here. We were asking for a 900 degree a second rotation, and here we're at just about 870 degrees. So we've only let off about 30 degrees a second on the command. And the D term sees, again, that we are accelerating away from our target very quickly. We're going very fast, and we're asking it to go a lot slower. So the D term starts kicking in very fast and spikes our motors, and then as the target actually starts moving a further distance away, the P term also catches up, and all of the motors spin up to the same thing the opposite way, the full speed. And what you're seeing here is they're not staying even because the weight balance on this quad is fairly poor, and it's trying to maintain stability in all three axes. So there's yaw and pitch that it's trying to compensate for through this as well, because I'm inputting a little bit of pitch on the sticks. So you're not going to get a pure result even though you're doing just a straight roll. The P term is pushes our speed down. As soon as we start getting closer, accelerating closer towards the target, our D term again is looking ahead and sees that we're accelerating quickly towards our target and starts telling us to slow down. And right about here, the P term is still driving us because we're still a far way away, and we haven't hit our target yet, but the D term sees that we're still closing in, and it's now pushing us the opposite direction. And so right about here, if we look at what these two terms are, you'll see that this P value and this D value are opposite each other, and the PID sum here is just about 0, so we're coasting. As we hit our target, the P term again drops to 0, and the D term will start to counteract this little bounce that we get. If I go over to this next one, I have just another roll, and you can see the similar thing, the error dropping, and the P term and the D term driving us through, and then partway there we're hitting another full throttle as it overshoots its target and then comes back and coasts through the middle. But on this one, on the recovery, you can see very clearly the D term leading the P term as we accelerate towards our target, and it pushes us away from that so we don't overshoot it as much. But we also have a little bit of oscillation here, and you can see the error is at its highest here as we start letting off the stick. And here we've dropped our command down in half, only asking for 500 degrees instead of 900 degrees. And then we actually overshoot here, and now we're 80 degrees the opposite side that we actually want to hit. So in this case, the quad has over slowed down and then needs to accelerate back up again to match the target that we hit, and you'll see then it overshoots again a little bit on that side before it settles out. So you can really see here where the D term sees that we're moving very quickly. We've just had this really big burst of throttle on this side that's going to be slowing us down, and the D term sees that we're moving before the P term really has even reacted, and keeps it from keeping that throttle pinned, which even as you can see, we already overshoot our target, that we don't overshoot it nearly as bad as it would have if we had kept powering through that whole time. And every time we approach the target, the D term here is ahead of where the the P term is. So right here, we've just passed through our 0 point. Our P term is also 0, but we're accelerating away from our target on this last overshoot, and the D term is going to fight that as we go up. Now on yaw, it's a little different. In current beta flights and for a while now, D term on yaw is completely disabled. We don't actually have a D term. And so here I'm doing a very big yaw spin, and you'll see what it looks like when we have very little control authority. Remember, in the roll, you'll notice that the motor's punched to full throttle for maybe only 30 or 40 milliseconds or something like that before we overshot our target, and then it had to restabilize the other way. In this case, when I'm sitting at idle and I begin asking for a 1200 degree a second yaw spin, our error goes down and our motors pin on opposite corners. And this is just about as much yaw as we can get. And again, you can see here where my weight balance, because I'm tail heavy, it's really affecting how much control authority I have, because I can only spin that motor up so much because it's trying to compensate for the pitch forward. So you'll see the error peaks out, but they just keep powering on, and the P term is the only thing that's driving us. There is no D term here at all, and we just slowly hit our target and it creeps up towards it, and there's no overshoot. Because this axis moves so slowly, just the P term, as we close in on it, the reducing of the P term, we have enough drag that the axis kind of takes the P term takes care of itself. And then in the recovery, same thing. I just start barely letting off the stick, so the error is growing the opposite direction because I'm moving the stick, and we shoot with the P term and then have everything zeroed out. And we really close in on we reduce our error to 0 very slowly. There's like no way to speed this up. Because I'm basically pegged at full throttle, I am at full authority through this entire move. So there isn't any quicker that I can ask the quad to move. Like if I increase my P term, I'm not going to increase my responsiveness here because it's already doing everything it can to hit my target. Now, one final thing that I wanted to draw attention to here, this is another roll, just like the others. You can see D term bleeding, the error grows and we get a punch of throttle, and then we coast through. And what we see here on the recovery looks like a lot of we're overshooting our target both directions. It looks like kind of a classic oscillation, and this you'll see when you have too much P term or not enough D term. But you want to keep in mind the whole control system when considering this, because what we have here is not something you can tune out because it's not driven by these PIDs here. This is not PID oscillation. And if you look at the stick, you'll see what happens is I have a lot of commands back and forth. The distance between each of these swings is only about 10 milliseconds. I'm not whacking the stick back and forth, but what happened here is I let go. I had the stick at full onto one side, and I just let off with my hands and let it auto center itself. And what you're seeing here is the stick swinging almost a half throw, 3/4 throw, just with its own mass and momentum, the springing it back into the middle. And the quad is responsive enough to respond to that, and you can see that here in the gyro trace. Just those couple milliseconds where it's whacked over to the side, that's enough to get a command in there, and we're accelerating a lot more, and then it's asking the other one, we're slowing down, and then we're accelerating and slowing down. So this is commanded oscillation. So you want to keep that in mind when you're flying and tuning. If you see, like if you're getting a lot of looseness and wobbles, you're flying straight and it's not keeping a line, be sure to make sure that it's not something that you're subconsciously causing, that you're not fighting with the sticks and causing this sort of effect. If you see that your sticks are wobbling back and forth and your quad is also wobbling back and forth, you're causing a lot of that yourself. And this is just the perfect example of that, where you would look at this and say, oh, my P term is too high, or I need more D term to counteract it. Nothing you do in the PIDs can fix this, because the radio was actually commanding this high speed oscillation, and the quad is just doing what it's told to do. So when you're doing tests like this, it's really good to be extremely clean on the sticks. When you're looking for I term and wobbles and you're flying forward, try to let off the sticks, just get it on a line and let it ride itself how it wants to be, so that you have a clean trace. You can see what the PID controller is doing completely on its own without you trying to fight it and compensate for it. And the same thing here with the rolls. Like I'm doing this roll only on one axis, as much as I can. Like, I'm obviously not hitting it perfect, but it's not a roll, yaw, spin, coordinated turn or anything like that. Really keeping it restricted to one axis, so you can see how our overshoots are, how we're hitting the targets. We can look at the error and look for oscillation. So here I can see that I've got a lot of overshoot, and I probably need a lot more D term or other settings to try and get rid of a lot of this overshoot and make it snappier. This feels, in the video, these flips don't look super oscillation-y, because that correction happens so quickly. It's only within 1 or 2 frames, and they still look and feel really clean, but they could be cleaner, and we could be hitting our target a lot closer right off the bat. And if we go back here to the first chart set that we looked at, where we have the RC command versus the gyro, it's really interesting that you can see the command delay very clearly here. We have this huge spike on this first bounce, where we're commanding a very positive direction, but we're still down here, and it takes some time for this to come. And when we bounce down to the low side, it actually just so happens to be about the same 10 hertz kind of cycle here, where we're hitting our low side just as we're hitting the peak. Now, this here isn't affecting this yet. We're seeing this first droop of the command where it's starting to slow down. That's here, so we're still basically 2 command samples back. Each of these straight line segments would be one S-bus command from the receiver, and that takes about 9 milliseconds for each S-bus cycle. So we can measure this in on our time here and see that this is about 10 milliseconds apart, and we have about the same. You can see we've got 2 clicks up on the command, and so that's about 18 milliseconds between these 2 samples here. And you can see where this peak is influencing that one, and this low is influencing this one here. 9, 18, about another 20 milliseconds. This peak, this command is causing this peak here, and this low is causing this low here. And so you can see an excellent example of where your command inputs being opposite of necessarily what your gyro is saying, and the PID controller can do this itself. And this is where you get reinforcing oscillations. The PID controller, if this, and remember, this is the stick command, this is not the PID controller that's doing this, but if this was the PID controller, you can see where if this value is high and the PID controller is very responsive to that and instantly pushes low, by the time that motor command, the motor spins up and the thrust pushes, and we actually see that response on the gyro, we're already opposite of where we were, and we're giving a very large command the opposite direction there. And so we can reinforce this oscillation if we're very, very overtuned.